Previously, we discussed Siemens, ABB, and MICOM's differential characteristics, noting their similarities in comparing operating to restrained current. The operating or differential current equation is similar, but the string current equation varies by relay. Today, we'll explore a new differential characteristic common in many stations, especially in cell 411L relays for line protection. Meanwhile, cell relays for transformer protection use the previously explained characteristic. We mentioned the equation for operating or differential current is similar among them, while the equation for the string current varies by relay. In this episode, we will discuss a new differential characteristic common in many stations, especially cell 411L relays for line protection. Cell relays for transformer protection use the same characteristic as before. So stay with us. Differential protection is used to protect areas with high accuracy and speed in isolating fault. Line differential protection aims to protect the area between all CTs at its ends, known as the differential operator. So stay with us. It is well known that differential protection is used when we want to protect a specific area with high accuracy and speed in isolating faults. Notice in this image that the intended goal of IM differential protection is to protect the area enclosed between all the CTs at its ends, and this area is referred to as the differential operate. Differential and breadth. The faults within this area are internal faults, while those outside the CT boundaries are external faults. The differential restraint area should remain stable and not trigger line differential protection. Differential protection, based on phase comparison, may fail to detect high impedance internal faults with minimal fault current contribution. It's crucial to select a method that handles city saturation, line charging current, or communication issues due to channel time delay, as these can reduce relay sensitivity. The relay may struggle to address each issue individually due to a single setting for all, challenging the balance between sensitivity to high impedance faults and avoiding false tripping. An appropriate method must be chosen to handle city saturation, line charging current, or communication issues due to channel time delay, which reduce relay sensitivity. The relay cannot distinguish each problem individually due to a single setting for all issues, challenging the balance between sensitivity to high impedance faults and avoiding false tripping. This affects safety and reliability. A new characteristic, polar characteristic or alpha and beta plan, also known as current ratio complex plan, is considered to solve each problem without affecting sensitivity. Instead of using Kirchhoff's current law, this relay calculates the remote to local current ratio, placing it on the alpha plan to determine fault location. All current values are directional, considering both magnitude and angle. This issue affects the safety and reliability of this type of characteristic. Therefore, there has been a consideration to create a new characteristic that allows me to focus on solving each practical problem without affecting the sensitivity of the relay. This new type of characteristic is referred to as polar characteristic or alpha and beta plan, and it can also be called current ratio complex plan. So, calculating the current difference using Kirchhoff's law, we calculate the remote to local current ratio. This ratio is placed on the alpha plan to check if the fault is within or outside the protected area. All current values are directional, having magnitude and angle. Each phase has a specific alpha plan, as do positive, negative, and zero sequence currents. This polar characteristic uses a 2D polar coordinate system, where each point's position is determined by its distance from a reference center, the pole. This is the radial distance. And there is an alpha plan specific to each phase individually, and similarly, there are alpha plans for positive, negative, and zero sequence currents. When I say that this operating characteristic is a polar characteristic, it means that it uses a two-dimensional polar coordinate system, where the position of each point in this plane is determined by the distance separating that point from a reference center called the pole. This distance is referred to as the radial distance. This distance is referred to as the radial distance. This distance is referred to as the radial distance. In addition to the angle of deviation of this ray from a reference line, this angle is called the polar angle. The radial distance here represents the ratio of any remote current to the local current, while the polar angle is the difference in angle between them. Unlike Cartesian coordinates, in traditional presentations, we used to show a diagram of the selection with the polar current diagram is more comprehensive. In relays with current and voltage inputs, the complex plane is represented using the impedance diagram. In relays with only current input, it's represented using the current ratio diagram. The operator denied. Denied. The polar current diagram is more comprehensive because it illustrates the behavior of the real and imaginary components together on the complex plane. In relays that have inputs for current and voltage signals, the complex plane is represented using the impedance diagram. However, in relays that have only one input for current signals, the complex plane is represented using the current ratio diagram. You can convert from polar coordinates, RF, to Cartesian coordinates, x, y, by using what are called trigonometric functions, such as sine, cosine, and tangent. The remote current vector divided by the local current vector will give me R as the magnitude at an angle F, which equals A plus JB, where A is the real part and JB is the imaginary part, for example. A complex number consists of a real part A and an imaginary part B. The real part A is found by multiplying magnitude R by the cosine of the angle. Magnitude R is the ratio of the remote current's magnitude to the local current's magnitude, and the angle is the difference between their angles. The imaginary part B is magnitude R times the sine of the angle. The vector value of R is magnitude R times cosine of the angle plus J sine of the angle, where J is the imaginary unit, equal to the square root of -1, or 1 at an angle of 90 degrees. Magnitude R is found with angle difference between remote and local current. Magnitude refers to scalar, not vector. Vector R is magnitude R times cosine of angle plus J sine of angle. Equation becomes R times cosine of angle plus J sine of angle, with R as a common factor. J is the imaginary unit, S squared 1, or 1 at 90 degrees. J squared equals 1, converting. Our cosine of the angle plus J sine of the angle. J is 1, R as A2 plus B2, angle as arctan BA, alpha as I remote, I local. Ray length shows remote local ratio. Polar angle shows angle difference. Thus, J squared equals the square root of -1 squared, which equals -1. The conversion from Cartesian coordinates to polar coordinates is as follows. The magnitude R equals the square root of A squared plus B squared, while the angle equals the inverse tangent of B over A. Now, the alpha plan represents the complex ratio of the remote current to the local current. Alpha equals I remote over I local, or arcs. The race length shows the remote to local current ratio, and the polar angle shows their angle difference. The x-axis is the real part, values A in the complex number, and the y-axis is the imaginary part, values B in the complex number. Local current flows into the line, and remote current flows out. If the current entering the line is at 0 degrees, the current leaving should be at 180 degrees. If the current entering is 5 amperes at 0 degrees, the current leaving is 5 amperes at 180 degrees. If local current for phase A is 5 at 0 degrees, phase B is 5 at 120 degrees, and phase C is 5 at 120 degrees, forming a positive sequence. If we assume that the current entering the line is at an angle of 0, then the current leaving the line should be the same, but at an angle of 180 degrees. This means that the phase shift between the two currents, the incoming current and the outgoing current in a normal situation, or in the case of external faults, is 180 degrees. If we assume that the current entering the line is 5 amperes at an angle of 0, then the current leaving the line will be 5 amperes at an angle of 180 degrees. The remote to local current ratio is 1 at 180 degrees. If phase A's local current is 5 at 0 degrees, phase B's is 5 at 120 degrees, and phase C's is 5 at 120 degrees. Phase A's current is 5 at 0 degrees, phase B is 5 at 120 degrees, and phase C is 5 at 120 degrees, forming a positive sequence. All currents are equal in magnitude. As for the currents, they will be of the same magnitude but at an angle of 180 degrees. Since the result is the same in all three phases, we only need to create the alpha plan once to avoid repeating it 3 times. When converting the magnitude of 1 at an angle of 180 degrees, the vector R will equal the magnitude R at an angle, plus the magnitude R at an angle. Here, the magnitude R is 1. Therefore, the equation will be R, which is 1 times cosine of 180 degrees plus J times 1 times sine of 180 degrees. Since cosine of 180 degrees is 1 and sine of 180 degrees is 0, the vector R will equal 1 plus J times 0. Thus, the value of A equals 1 and the value of B equals 0, where A represents the real part and B represents the imaginary part. This point represents a state indicating that in a fault, all currents feed the fault point. Current entering is at 0 angle. Current leaving at 180 degrees. This is an internal fault. Ignoring non-fault errors, the system state point lies on the A-axis or real axis. A changes with fault type and feed method. Since all currents are entering the line, these currents are at an angle of 0, but it is not necessary for both currents to have the same magnitude. This situation is called an internal fault in feed. If we ignore all sources of errors from operational issues, not actual fault conditions, the point showing the system state lies along the A-axis or the real axis, and the value of A changes along the axis based on the type of fault and the way it is fed. The value of A is as follows. If the value of A is -1, it represents the ideal condition, which covers external faults or load conditions. If the value of A is greater than 0, it represents the ideal condition. The value of A is as follows. If the value of A is -1, it represents the ideal condition, which covers external faults or load conditions. If the value of A is greater than 0, it represents the ideal condition. Internal fault and feed. These are fed from two sources or from both ends, the local and the remote end. As for the internal fault outfeed, the value of A is less than 0. If part of the fault current flows out of the line towards the local end only, then the value of A will be less than -1. However, if part of the fault current flows out of the line towards the remote end only, then the value of A will be between 0 and -1. The term internal fault outfeeds refers to certain faults that are fed from only one side, where the fault condition forces the fault to go outside the line towards the load. Due to high impedance internal faults, this means that the voltage current will be distributed between the short circuit and the load, and in this case, the voltage current is less than the load current. The value of the angle is between 180 degrees unless it differs. This means that I can deal with these special and difficult cases that the traditional method fails to detect. In internal faults, the angles of local and remote currents depend on the voltage source and impedance angles up to the fault point. These impedances differ from both sides, so the angles won't be identical. They vary within plus or minus 30 degrees. External voltage, load, and internal faults fed from one side remain unchanged in this diagram for the same reason. In normal operation or external faults, remote and local currents aren't equal. The point indicating an external fault shifts, varying with fault type and location. Communication time delay causes a phase shift between local and remote currents. Communication errors cause load and fault area expansion. The load and internal fault from one side remain unchanged for the same reason. In normal or external fault conditions, remote and local currents won't be exactly equal. The point at 1 indicating an external fault will shift based on fault type and location. Communication delay causes a phase shift between local and remote currents, requiring timely and accurate arrival. Non-ideal channel symmetry leads to inevitable timing errors. This delay compensation error expands load and fault areas. Worst case, combined angle errors from impedance and delay alter the final shape, widening internal fault angles. Our goal is to monitor system behavior. As for the communication time delay, its presence will result in a phase shift between the local and remote currents. The value must not only arrive correctly from the other end, but also on time. Due to the non-ideal symmetry of the communication channels, errors in the arrival time of each current to the other end will inevitably occur. The effect of this channel time delay compensation error will cause the load and fault areas to expand in this manner. In the worst case scenario, if the angle errors of the remote and local currents caused by the impedance combine with the angle errors resulting from the communication time delay, the final shape will look like this. Notice the widening of the angles of the internal fault due to the cumulative angle errors. The goal we are aiming for is to monitor the behavior of the system. With all these expected practical errors, we then want a drawing that is able to accommodate all these expected errors so that we can achieve a balance between safety and sensitivity at the same time. As shown in this picture, we were able to control an area to be confined within this shape while an area is outside it. It's easy to shape the ideal operating characteristic for the alpha plan. The 87-line angle sets the restraint area angle. The 87-line radius sets the outer restraint area. The inner radius is the inverse of 87 LR. The alpha plan has operating and blocking areas. The blocking area includes non-operating cases, excluding trips. Specialists used simulations to compare percentage differential and alpha blank characteristics for safety and sensitivity. They identified boundary values for I differential and I restraint on the alpha blank and applied them to the percentage differential. So it's 1/87 LR. Thus, the alpha plan can be divided into two areas, the operating area and the blocking area. The blocking area, or the restraining area, includes all cases where the relay should not operate, excluding all actual trip cases. Some specialists conducted an experiment using computer software simulations to compare the percentage differential characteristic with the alpha blank characteristic, aiming to find out which one is safer and more sensitive. They found a large number of boundary values for I differential and I restraint on the alpha blank characteristic, and then reflected these values onto the percentage differential characteristic. Then these values were reflected onto Then, a large number of boundary values for I differential and I restraint were found on the percentage differential characteristic, and these values were then reflected onto the alpha blank characteristic. You can refer to this research to know the final results and delve into more details regarding this matter. The principle of operation of differential protection in the alpha plan is that it will work when two conditions are met simultaneously. The first condition is that the value of the differential current is higher than the minimum threshold value set, which can be 87LBB, 87L2B, or 87LGB. The second condition is that the value of alpha is outside the restraining zone, or this region is non-reactive, and the restraining region reacts if local and remote current over 5%, and the value of alpha is beyond the restraining region when outside the radius and block angle boundaries, and both are in setting. The alpha value is outside the L region when the point is outside the L, and outside the block angle boundary. Both values are present in the sting. When we want to test the relay, we need to decide whether this test is a single terminal test with one device injecting local and remote current, or if we are testing this relay using a multi-terminal characteristic test, meaning there are two injection devices, each connected to one terminal. When testing the relay, it asks for single or multi-terminal mode. Assume testing relay in single terminal mode, then 87 on phase A, 87 LA, using accelerator quickset software with cell relays. This setting is used where we find that the minimum phase current differential value is 0.3 per unit. Let's assume we want to test the characteristic of this relay in single terminal mode, and then test 87 on phase A, meaning 87 LA, using the accelerator quickset software that communicates with cell relays. This setting is used where we find that the all minimum phase current differential value is 0.3 per unit. Point phase, radius 2, angle 200 degrees. Apply. The radius is 2, and the block angle is 200 degrees. We apply these to the alpha plan. The outer radius is 2, and the inner radius is 1 and 2. The 200-degree angle splits 100 degrees from the real axis to the positive imaginary part, and 100 degrees to the negative imaginary part. In a single terminal test, the relay assumes one phase's current is local, the next phase's is remote. Testing 87L on phase A means phase A's current is local, phase B's is remote, as the remote current can't be injected from the other side. In the inner radius, the 200-degree angle splits similarly. 100 degrees from the real axis to the positive imaginary part, and 100 degrees to the negative imaginary part in a single terminal test. The relay assumes that one of the currents of the three phases is the local current, while the current of the next phase is the remote current. This means that if you choose to test 87L on phase A, the relay assumes that the current of phase A is the local current, while the current of phase B is the remote current, because in this case, the remote current cannot be truly injected from the other side. Similarly, when testing 87LB, the current of phase B is the local current, while the current of phase C is the remote current. When testing 87LC, the current of phase C is the local current, while the current of phase A is the remote current. As for 87LQ, it represents the differential negative sequence current. When testing LAT7LC, the current LAT-C is the local current, and the current LAT-A is the remote current. As for LAT7LQ, it represents the differential negative sequence current, and it is injected directly. So we don't need to perform any calculations, equations, or matrices. This means that if it equals, we inject it on phase A as it is. As for the, it represents, we inject the A as it is. But the L represents the L. And be here. IA is local and IB is remote. There are three tests we will conduct to check the differential protection in the alpha plan. First, the pickup setting test, 87 LBB. Second, the radius setting test, 87 LBR, 87 LBB is the pickup setting test, and 87 LBR is the radius setting test. Symbol is inject lower current than pickup, gradually increase current until pickup signal or trip. After pickup signal or trip, reduce current until signal disappears and record drop-off current. Inject double. Pickup current, measure trip time, should be instantaneous in milliseconds. Inject 0.2 amperes at 0 angle on phase A. Relay read. Pick up the signal on the ID, or it closes the ID. After the pickup signal appears, we gradually reduce the current until this signal disappears and record the drop-off current value. After that, we inject a value that is double the pickup current and measure the trip time, which should be instantaneous, meaning in milliseconds. When injecting 0.2 amperes at a 0 angle on phase A, the relay will read the following. The local terminal current for phase A will be 0.2 at a zero angle, which is the value I injected. As for the remote terminal current for phase A, it will be 0 at a zero angle because no current was injected on phase B. The differential current for phase A will be 0.2 at a zero angle, which is the vector sum of the local and remote current values. For alpha's value in A7LA, it is 0 at a zero angle, appearing when local and remote currents exceed 5% of I nominal. Choosing phase A for the differential test causes the relay to trip if current increases on phase A or B, as the relay assumes phase A is local and phase B is remote. Increasing phase C's current during phase A, testing won't be detected, even with higher injection. If K at angle alpha is 0, it's inactive, so the relay only trips if the value exceeds a threshold, behaving normally. Injecting 0.5 amperes at zero angle on phase A and 0.5 amperes at 180 degrees on phase B simulates normal load conditions, and the relay reads accordingly. The relay assumes phase A is local and phase B is remote, so increasing phase C's current during phase A, testing won't be detected even with higher injection. If K at angle alpha is 0, it's inactive. Therefore, the relay will rely on just one value. And it must be higher than a certain threshold to issue a trip signal. This means that the relay behaves as if it is in a normal state. When injecting a current of 0.5 amperes at a zero angle on phase A and 0.5 amperes at a 180 degree angle on phase B, we represent the load current condition in a normal state, and the relay will read the following. The injection current on phase A is 0.5 at a zero angle, and the injection current on phase B is 0.5 at a 180 degree angle, which is the same value coming from the injection device as it is. The local terminal current for phase A is 0.5 at a zero angle because the relay considers phase A to be the local current. The relay sees phase B as remote, when phase A's differential current is 0, based on vector sums at 0 and 180 degrees. For 87LA, K is 1 at 180 degrees, ensuring stability and no trip signals. To test the outer radius of 2, set remote current at 0.5 and increase local current beyond 0.5 to leave the restraint area, plus 0.5 at a 180 degree angle, which is the vector sum of the remote and local current values. As for K at angle alpha for 87LA, it equals 1 at a 180 degree angle, derived from 0.5 at a 180 degree angle over 0.5 at a zero angle. This factor or value is usually found by dividing the smaller current by the larger current, regardless of which is the local or remote current between them. Since the value of K at angle alpha is within the restraint area, this means that the relay should remain stable and will not issue any trip signal. To test the value of the outer radius, which equals 2 according to the setting, we will fix the value of the remote current at 0.5 as just an example, and then we will gradually increase the value of local current so that it becomes greater than 0.5 until we exit the restraint area to the left. The relay will issue a trip signal when the injection current exceeds I local by 1 ampere or plus or minus 5% of it. At that point, the value of I local to I remote, that will equal 1 to 0.5 or 2, which is the outer radius that needs to be tested. To test the inner radius value, which equals the reciprocal of 2, I 0.5, we fix the local current at I 0.5 and then increase the remote current at I 0.5. To exit the restraint area to the right, the relay will issue a trip signal when the injection current reaches I0, which is 1 or plus or minus 5% of it. At that point, I local to I remote equals 0.5 to 1. The inner radius, to test the outer radius, fix the remote current and increase the local current. The relay reads by dividing the smaller by the larger value. A small result indicates the inner radius. A large result indicates the outer radius. Local current is 0, remote current is 180 degrees. In the test, again, we adjust the value, and the relay calculates by dividing the smaller by the larger value. A small result indicates the inner radius. A large result indicates the outer radius. We didn't change the angles. Local current is 0 degrees, remote current is 180 degrees. For the relay to trip based on the alpha characteristic, it must meet 3 conditions: angle, minimum threshold, and radius. If one condition isn't met, we ensure 2 are met and test the third. A small division result indicates the inner radius. A large result indicates the outer radius. Angles remain unchanged. Local current is 0 degrees, remote current is 180 degrees. For the relay to issue a trip signal based on the alpha characteristic, it must meet 3 conditions: angle, minimum threshold, and radius. If one condition is not met, the third is tested. A trip signal occurs if K exceeds the outer radius, I local over I remote, in 2 scenarios: increasing local current with fixed remote current, or decreasing remote current with fixed local current. And we test point K left, K outer radius, I local, I remote, fixed remote current, increase local current, fixed local current, decrease remote current, point K right, K inner radius, I locker, I remote, fixed remote current, decrease locker current, fixed locker current, increase remote current, block angle test, set local, 0 degree, remote, 180 degree. So move point K to the right, and it will issue a trip signal if the value of K exceeds the inner radius, which equals I locker over I remote. In 2 cases as well. The first case is fixing the remote current and then decreasing the locker current, or the second case is fixing the locker current and then increasing the remote current. This is all part of the national revival. To test the block angle setting, we inject 2 currents, one on the local current and one on the remote current, with equal values greater than the differential pickup value. Then we set the local current at a 0 angle and the remote current at a 180 degree angle. And your remote current is at a 180 degree angle. Then we change the angle of the local current counterclockwise until the relay issues a trip signal, which means that this point has entered the operating area. After that, we change the angle of the local current clockwise until the relay resets, indicating that we have entered the restraining area. We then record in the report the limits of the angles for the operating and non-operating areas, and we can find the expected limits of the restraining angle. Expected 180 gram, 87 lBA over 2 to 180 gram plus 87 lBA over 2. These limits, or this area, is called the alpha angle range. If 87 lBA in the setting, you're at 200 degrees, the alpha angle range will be from 180 degrees, 200 over 2 to 180 degrees plus 200 over 2. So the operating angle will be from 80 degrees to 280 degrees via 0, while the restraining angle will be from 280 degrees to 80 degrees via 180 degrees. Error margin plus 5 degrees. We apply the same steps for the other phases at 0.5 amperes at 100 degrees. Operating angle 80 degrees to 280 degrees via 0. Restraining angle 280 degrees to 80 degrees via 180 degrees. The expected error margin according to the manual is plus or minus 5 degrees. We apply the same steps for the other phases. Now let's move to a new case where we inject 0.5 amperes at a 100 degree angle on the locker current, and 0.5 amperes at a 180 degree angle on the remote current. The relay will read the following. The value of the local terminal current for phase A that the relay will read is 0.5 at a 0 angle, because the relay considers phase A to be the reference value. Therefore, the relay will always set its angle to 0. As for the remote terminal current for phase A, it is 0.5 at an 80 degree angle for phase A. It is at an 80 degree angle. The angle of 80 here is the angular difference between the local and remote currents, assuming that phase A is at a 0 angle because it is the reference. The relay subtracted 100 degrees from both currents. As for the differential current for phase A, it is 0.765 at an angle of 40 degrees, which results from the vector sum of the values of the local and remote currents, which equals 0.5 at a 0 angle plus 0.5 at an 80 degree angle, plus 0.5 at 80 degrees. As for the value of K at an alpha angle for the 87 LA, it equals 1 at an 80 degree angle, which results from 0.5 at an 80 degree angle over 0.5 at a 0 angle. This is the result of dividing the small current by the large current. K at angle alpha is on the boundary of operate and restrain regions. Injecting 1 ampere at 0 degrees on phase A and 0.5 amperes at 180 degrees on phase B, the relay reads local terminal current for phase A is 1 ampere at 0 degrees, as phase A is the local current. Remote terminal current for phase A is 0.5 at 180 degrees, as phase B is the remote current. Differential current for IA is 0.5 at 0 degrees. 3.5 at 0 degrees is the vector sum of local and remote currents, equaling 1 ampere at 0 degrees plus 0.5 ampere at 180 degrees. K at angle alpha for 87 LA is 0.5 at 180 degrees, from 0.5 at 180 degrees divided by 1 at 0 degrees. And 3.5 at 0 angle, and 3.5 at 0 angle. This is the vector sum of local and remote currents. 1 ampere at 0 degrees plus 0.5 amperes at 180 degrees. K for 87 LA is 0.5 at 180 degrees, from 0.5 at 180 degrees divided by 1 at 0 degrees. This results from dividing the small by the large current, regardless of which is local or remote. Injecting 0.5 amperes at 0 degrees on phase A and 1. When injecting 0.5 amperes at 0 degrees on phase A and 1 ampere at 180 degrees on phase B, the relay will read the following. The local terminal current for phase A is 0.5 at 0 degrees. The value of the remote terminal current for phase A is 1 ampere at 180 degrees, same as phase B. The value of the differential current for phase A is 0.5 at 180 degrees, from 0.5 at 0 degrees plus 1 at 180 degrees. As for the value of K at angle alpha for the 87 LA, it equals 0.5 at 180 degrees, from 0.5 at 0 degrees divided by 1 at 180 degrees. Dividing the small current by the large current, regardless of local or remote, plus 1 plus 8 degrees. K is 0.5, derived from dividing small by large current. Local is 0.5A, remote is 1A, and vice versa. K is small over large current, always Mach 1. Shows reading K local and remote are relative. At the local substation, current is 0.5A, local and 1A remote. At the remote substation, current is 1A, local and 0.5A remote. Thus, K readings differ between the two relays. K is small current over large, so K 1. Some engineers are confused. Is K I remote, I local, or I local, I remote? The remote current is 0.5 amperes, so the reading of K will differ between the two relays on each side. K is the small current divided by the large current, so the value of K will always be less than or equal to 1. Engineers are confused about calculating the value of K. This confusion arises because the 311L manual says K is I remote over I local, while the 411L manual says K is I local. Over I remote. Both represent the radius for loopback protection. Is it I local or I local over I remote? The reason for this confusion is that the 311L manual states that the value of K equals I remote over I local, while the 411L manual states that value of K is I local over I remote. Both represent the radius when selecting the loop back for protection. When injecting a current of 1 ampere at 0 degrees on phase A, the relay will read the following. The local terminal current for phase A will be 1 at 0 angle, which is the same value that was injected from the injector. The remote terminal current for phase A will also be 1 at 0 angle because of the loopback. The loopback takes the value of the local current and reverses it exactly to the remote current. The differential current for phase A will be 2 at 0 angle, which is the result of the vector sum of 1 at 0 angle, which is the local current plus 1 at 0 angle. It is a remote current, but the value of K at an alpha angle of 87 LA will be 0 at an angle of 0, as in this case the value of K was not calculated because the point fell outside the Aston region, which means that it moved towards the positive real bar. Therefore, the value of K is only calculated if the point is within the boundaries of the restraint area. With that, we conclude today's lecture, and our final prayer is that all praise is due to Allah, the Lord of the worlds. Stay tuned for the next episode where we will explain high impedance differential protection. See you soon. For example, protection. See you soon.